Hey Pre-Calculus, today we're going to go over inverse functions, and you can find that in chapter 3.6 of your ebook. So first off, what is an inverse function? An inverse function is something that undoes the action of the original function, right? If you've got your domain and you've got your range, you got point in the domain, you got another point in the range. A function maps a point from the domain to the range. Now, what does an inverse function do? An inverse function does the exact opposite. An inverse function takes the guy here and maps him straight back to where it was before, right? It undoes the action. Hence this nomenclature you see here. If this is your function, then the inverse function is this guy right here, right? Note that f takes x and turns it into y. The inverse function takes y and it turns it into x. It's a bit like if you think of a directions to, say, to get to a store. If you follow the directions to get to the store, well, what do you do when you want to come back home? Well, you reverse the directions that you just got, right? You follow them in the exact order, in the exact opposite way. And that would be the inverse of the directions to the store. Instead of taking you from the house to the store, now the inverse takes you from the store to the house. So one of the things that we want to keep in mind with the inverse function is that note that the domain of the function, all the values of x, and the range is y. Well, what about for the inverse function? Well, the inverse function, the domain are now all the y values, and the range is now all the x values. Basically, what's happening is the domain and the ranges are swapping when you go to the inverse functions. So for right here, for instance, we have the square root of x plus 1. What's the domain of this function? Well, we can't take the square root of a negative number, so therefore x has got to be greater than negative 1, right? Because if you plug in negative 1, you get 0. We can take the square root of 0. Not a problem. So the domain is negative 1 all the way to infinity. And we include negative 1. And there we go. Now what about the range of this function? This is just the square root function shifted to the left by 1 unit. So it's not moving up or down. So typically the range of this function is 0 to infinity. So the range equals 0 to infinity. You plug in negative 1, out it's going to come as 0. Alright, so now what about the other way? The range... let's go with the domain of the inverse. Well, that's going to be the range of the previous one, 0 to infinity. And now what about the range of the inverse? Well, that's going to be the domain of the previous one. Just like that. Okay, you see how they correlate with each other. Okay, so for number 2, we have to keep one thing in mind for this one that I have not talked to you about yet. These functions must be 1 to 1 because we need a predictive quality for the inverse function, or for the function of an inverse. So note, 1 to 1, that means it has to pass the horizontal line test. This one fails. So what we're going to do is just take the right portion of the domain. Like, we're only going to take that one. We're going to ignore everything else. So what is the domain of the function? Well, that's going to be 0 to infinity. What's the range of the function? Well, it's also going to be 0 to infinity. You can just kind of see from inspection. Right. So again, for the reason the domain is not including all these numbers over here on this side is because we are just not going to look at those. We're going to pretend they don't exist. You could have easily gone from negative infinity to 0 if you wanted, but in this class we're always just going to pick the right side. And again, this is so that the inverse function will have a predictive quality. Alright, and so the domain of the inverse equals 0 to infinity. And then the range of the inverse is going to also be 0 to infinity. Okay. So what about this function here, 1 over x minus 2? Well, we do note that this is the inverse function shifted to the left by, to the right by 2. This function is 1 to 1 when you look at the graph. It looks like this. And you can see this function will pass the horizontal line test everywhere. Alright, so what is the domain? Well, the only thing that we've got to worry about as far as the domain is concerned is that x cannot equal 2, because we don't want to divide by 0, so x cannot equal 2. That's the only thing we have to worry about. So what is the domain of the function? The domain of the function is all real numbers except for 2. And that can also be captured by writing it in this format. Negative infinity to 2, open parentheses, union 2 to infinity, right? They both mean the same thing. Alright, now what about the range of the function? Well, note that's when you look at the graph here, you just can't, 0 is not included, but all the other numbers are. So the range is all real numbers except x cannot be 0. And you could write this as negative infinity to 0, open parentheses, union 0 to infinity. Right, and that is a perfectly acceptable way to write it. Now what about the inverse? Well, that's going to be all real numbers except for 0. Just like we've talked about before. And then the range of the inverse well, that's going to be all real numbers except for 2. Alright, and so this number 4, it's more just kind of a hypothetical. We're given the domain and we're given the range. For a actual graph function, this might not make the most sense, but this is just a, so to make sure we have the right understanding. What is the domain of the inverse? Well, that's going to be simply 1 to 8, right? That where all the numbers in between 1 and 8. And then what is the range of the inverse? Well, that's simply the domain, the numbers 1, 2, and 3. And that's how that works. Just like we were doing before. Okay, cool. As I've already talked about, a inverse function undoes the action of the original function. And so how do we know if two functions are inverse functions? We know by the following expression, right? The f composite g of x, well, this is f of g of x equals x. So basically, if this is true, and then if this is also true, right? You know, putting little question marks because we're not saying that because that's only true if they're inverses. If you go through that and it turns out that it doesn't equal x, then you don't have an inverse. So you're not setting it equal to x, you're testing it. You're testing it to see if it equals x. All right, so determine the following functions are inverses of each other. So we got to make sure we test it in both directions. So f of g of x, right? That's f composite g. So this would be f of x squared. And then we plug that in. And so that is the square root of x squared. Square root of x squared is simply x, right? And so note that we would have to put a domain restriction on g, but that's all right. For this to be totally correct, let's just say such that x is equal to or greater than 0. Let's assume that's the case. And now let's look at the other direction, g of f of x. What's going to be g of this guy there. And so we're going to be putting in like this. So the square of the square root is simply x. Huzzah, it works. Okay, so yes, they are inverses of each other. All right, so let's go ahead and take a look at the graph. All right, so we got f of x, which is x squared, and then g of x, which is the square root of x. I might have these swapped, but as long as they're, but that's all right. Actually, I think I do have these swapped. Let me go ahead and, there we go. So note that we had to put a domain restriction on g. And so let's go ahead and include that. So we got to put it that such that x is greater than or equal to 0. And there's our domain restriction. All right, so note that there's a nice little symmetry between these two functions. They seem to be mirrored about a particular line. And what line is that being mirrored about? Well, it seems to be mirrored about y equals x. Now that's interesting. Let's go ahead and make that there we go. Interesting. Okay, I wonder if that's going to be important later. All right, let's look at the next one. F of x equals x squared minus 2, and g of x equals the square root of x plus 2. So let's determine if they're inverses before looking at the graph. So f of g of x and so again, what is g of x? That's g of x right there. So f of the square root of x plus 2 just like that. All right, and so in here we've got the square root, the square of a square root, so it's become x plus 2 minus 2. And what are we left with? We're left with x. Great. Now let's check the other direction. G of f of x. And so we get G of this guy there. X squared minus 2, which equals this guy right here. Alright, so you can clearly see that we've got a -2 and a +2. Those go away. We're left with the square root of the square, which is just going to be x itself. Let me go ahead and move this down here so that you don't interfere with the space for number 4. Alright, great. That works out. Let's look at the graph of this. Alright, so I got these guys functioned. Once again, we got to make sure that we make sure both functions are 1 to 1. We're going to put in that domain restriction. So let's go ahead and put that on right here. So in order for this guy to be 1 to 1, you can clearly see that x must be equal to or greater than 0. Like so. Alright. And so now we've got this strange symmetry appearing again. Y equals x right there. Now isn't that something, huh? Wonder if that's going to be important later. Alright, so let's look at number 3 here. We've got the inverse function 1 over x, and for f, and then for g we also have the inverse function 1 over x. I wonder if the inverse function will be its own inverse. Alright, so this one we're just going to do f of g of x. We're only going to do f of g of x because note that g of f of x is exactly the same thing because they're exactly the same function. So what is g of x? Well, that's this guy right here. And so we're really saying, well, what is f of 1 divided by x? And so this is 1 divided by 1 over x. That's what that turns into. We got a fraction within a fraction. Let's get rid of that. So note, when we do that, this guy cancels with this guy. And what are we left with? We're left with just x. Surprise, the inverse function is its own inverse. But wait, that should be no surprise to anyone at all. Alright, so let's take a look at a graph of this function. Alright, so I'm only going to graph f since g would be the exact same graph. We notice that this graph does have plenty of symmetries, but let's look at the line y equals x, since that seems to be playing some kind of role. And indeed, that is still going on here. It looks like the inverse function is self-symmetric about the line y equals x. Interesting. I wonder if the symmetry property is going to be important. And now for number 4. We're going to look at f of g of x again, because that's how we test these things. So what is g of x? Well, that's going to be this guy right there. And so what we're really looking for is what is f of x minus 2 divided by 2. So we're going to plug that into our f over here. So this becomes 2 divided by, let's put parentheses here as a placeholder, x minus 2 over 2. And we got a little fraction within a fraction. Let's go ahead and make that disappear by multiplying top and bottom by 2. And we're going to distribute both of those, and so we're going to have 4 divided by x minus 2 minus 6. Keep in mind you got to distribute that 2 to both terms. to this guy, and then to that guy. And so we have 4 divided by x minus 8, and this does not equal x, therefore they are not inverses. And there is no reason to check the other direction because we've already concluded that one is not the inverse of each other. We're done. Alright, yeah, we can go ahead and take a look at a graph of these. And here's our graph. Note there is not much symmetry going on in between these two guys, and if I just throw in the line y equals x, we note that there is no symmetry about the line y equals x, and on account of these guys not being inverses. So note that kind of what I've been trying to tell you guys is that if you see a graph of two functions and you notice a symmetry about y equals x, well, then there's a really good chance that the graph, that those two functions that are being graphed are in fact inverses of each other. All right, so back on this handout, let's keep going on. So now we've gone over how the domain and range of a function swap when you move to the inverse of the function. We've gone over how the function has to be 1 to 1, right? It's got to pass the horizontal line test in order to have a function, and if it does not, then we have to do a domain restriction on the function. We've gone over how to verify if two functions are inverses of each other by simply popping one function into the other and testing to see if we get x as the result. Keep in mind, x by itself is the identity function. What we're going to check now is to see, well, given a function, how do you find its inverse? And we'll find it's really not too terrible. What we have to do is, first, you're going to swap the y and the x values as said right here. So for this guy, what we do is, because this is y equals f of x, we're going to say instead x equals the square root of y minus 1. Well, technically, the first thing you should do is check to see if it's 1 to 1. This guy is a 1 to 1 function, so we don't have to worry about anything. So next we simply solve for y. So, you take the square of both sides. We got y minus 1, add 1 to both sides, and we end up with y equals x squared plus 1. And now we just set that equal to the inverse. Just like that. I'm going to leave the graphing of these two functions in Desmos for you as an exercise, but I do encourage you to pause the video, go to Desmos, and graph both of these functions and verify that they are in fact symmetric about the line y equals x. Alright, number 2, note this is already a 1 to 1 function, so we don't need to do a domain restriction. So we're going to follow the directions. We're going to say, okay, x equals 1 over y minus 2. Solving for y. Y minus 2 equals 1 over x. Add 2 to both sides, and we get the inverse shifted up by 2 units. And so our inverse function equals 1 over x plus 2. There we are. That's it. Alright, so go ahead and press the pause button, graph both these functions into Desmos, verify that they are symmetric about the line y equals x. Alright, so for number 3, f of x equals x plus 2. Follow the directions. So we say x equals y plus 2, and then just y equals x minus 2. So what is the inverse function? It is x minus 2. Right, so we've got a linear function with a slope of 1 being shifted up by 2, The inverse is just being shifted down by 2. Graph both these lines in Desmos. Verify they're symmetric about the line y equals x. Alright, so for number 4, we follow the directions. X equals y plus 2 over y minus 1. Alright, so this one's a little tricky, but we can figure it out. Multiply both sides by y minus 1, so we get y minus 1 here, and then like this. Next, we're going to distribute this x value here to this guy and then to that guy. So we have xy minus x equals y plus 2. So again, what we're trying to do is we're trying to isolate the y's on one side and send all the x's to the other. So we're going to go ahead and keep this y function over here. We're going to move this guy over to the left, and then this guy we're going to move to the right, and we're going to keep that guy over there, right? That's how we're going to arrange things. So we've got xy minus y equals x plus 2. Right, so we've got all the terms where we want them now. Alright, so let's go ahead and finish this guy off. We're going to factor a y out on the left side, so we have y times x minus 1 equals x plus 2. I'm going to bring this over to the side here. Divide both sides by x minus 1, and we have y equals x plus 2 divided by x minus 1, and that is the inverse function. Just like that. Cool. All right. Graph the function and its inverse in Desmos. Verify that they are in fact symmetric about the line y equals x. Okay, so plot. On this last one, this last example here, we're given the function, and we're asked to plot the inverse. So we don't know exactly what the function is, but we know what the graph of the function looks like. So what would the graph of the inverse look like? Well, it's just going to be symmetric about this line. So we know that if it's symmetric, you know, if you're looking in a mirror and you're touching the mirror itself, where is your reflection touching? The same points that you are touching, right? So here, here, and here, right? If your function does not pass through these 3 points, you know it's wrong. And then everything else, you just kind of reflect it over. Kind of note that the x and y values are swapped. So you should get something like this, and then over here, about right there. And that's really all there is to it, right? Whatever your x and y value are at this point, at the symmetric point, it is y and x, right? They get swapped. That's all that's going on there.